Okay, in this video I'm going to talk about the nth roots of unity, and we've actually already seen this in the case n equals 4. So recall that you had I, but if you multiplied it by itself, I squared is negative 1, I cubed was negative I, and I to the 4th was 1, and then it just wraps back around on itself. I to the 5th is I again, negative 1 again, negative I, and 1 back and forth. And this time I've plotted it on the unit circle, and they all are on the unit circle, right? And notice that they're evenly spaced, and there's this nice angle of 90 degrees or pi halves separating each number. So we can understand this geometrically. The number I is equal to e to the I pi halves, right? It has unit length, so it's on the unit circle. So the r that would be here is just 1, and the angle is pi halves. So multiplication by r e to the I theta, recall, if you're multiplying a number by r e to the I theta, you're scaling by r and you're rotating counterclockwise by theta. So multiplying by I, you rotates the entire thing counterclockwise by 90 degrees, and it scales it by 1, right? So it doesn't scale it at all, it just keeps the same length. So in particular, if you multiply I by itself, it should take I, it should rotate it by 90 degrees counterclockwise, and it should just leave it at that. And that's indeed what it does. Multiplying I by itself takes you to negative 1. If you multiply by I again, you should again take this point, rotate it by 90 degrees counterclockwise. That takes you to negative I. And applying I one more time takes you back. And of course, multiplying 1 by I rotates the number 1 off the real axis into the imaginary axis and turns it into I. So there are a lot of nice properties here. So, if we're just thinking about it, you want to see what this looks like in polar coordinates. I is e to the I pi halves. If you square it, that's going to be e to the I pi halves times e to the I pi halves, which is e equal to e to the I, so product of exponents sums the exponents. That's I pi halves plus I pi halves, which is just e to the I pi, and that's exactly what I squared is, which makes sense because it's at an angle of pi, and it's of unit length. I squared is negative 1, right? And then again, I cubed would be I times 3 pi over 2, and I to the 4th would equal e to the 2 pi I. And remember that e to the 2 pi I is equal to 1 because you've gone around the circle completely and you're right back to 1. And in fact, any integer multiple of 2 pi would work here too. Yeah, so e to the 2 pi I times any integer k is always going to equal 1 because it means you've done k full revolutions counterclockwise around the circle. Or even if k is negative, that would mean going clockwise. So there's some interesting things to notice right off the bat. These 4 points are closed under multiplication and form a cyclic group. That's something I've already mentioned, right? If you multiply any of these 2 points with each other, any of these 4 numbers, 1, I, negative 1, negative I, you'll get back to one of the other 4. They form a group. What are the inverses here? Well, 1 is the identity element of the group. The inverse of I is whatever you have to multiply I by to get to negative I. I'm sorry, to get to 1, to get to the identity element, which is negative I. So these two are inverses of each other. And then negative 1 is its own inverse. Negative 1 times itself will give you the identity element 1. So this does indeed form a group. It is a cyclic group. It's generated by I, as we've seen, right? That just means that you keep multiplying I by itself, you'll eventually run through the entire group. And it does have 4 elements in it. So this is the cyclic group of order 4. There's only 1 up to group isomorphism, but it's a nice way of seeing it embedded in the complex plane. In fact, on the unit circle in the complex plane. And finally, notice that taking any one of these numbers to the 4th power, so 1 to the 4th power, I to the 4th power, negative 1 to the 4th power, I'll put that in parentheses, and negative I to the 4th power will always give you 1. 1 to the 4th is 1, I to the 4th right here is 1, and you can see it in the picture. Negative 1 to the 4th is of course 1. It's not the most efficient way to get to 1 once you're at negative 1, but it'll get you there. And negative I to the 4th is in fact also equal to 1. And by the way, before I move on, let me just mention I said I was a generator for this cyclic group. Also, technically negative I is a generator, because if you If you start with negative I, there's your negative I. If you square it, then the minus signs will cancel. You'll get I squared, you'll get to negative 1. If you multiply by negative I again, you'll get I. And then if you multiply by negative I again, you'll get 1. So actually, either this or this could be the generator, for those of you who know something about group theory. Well, now there's nothing special about the number 4 here. We've seen a cyclic group of order 4 embedded, but you can actually play this game with any other number. You can consider the third roots of unity, where they're kind of evenly spaced points. And notice that these things form the vertices of regular polygons. So let me just go back here. Obviously, if you connect these vertices, what you're going to get is a perfect square embedded inside the unit circle. Here you would get an equilateral triangle if you're considering the third roots of unity. These are the numbers, for example, this would be e to the I 2 pi over 3. And this would be e to the I 2 pi over 3 times 2. And then once you multiply it by 3, e to the I 2 pi over 3 times 3 would just be e to the I 2 pi, which is, of course, just takes you back to 1. So these are called the so-called third roots of unity. And if you take any one of them to the third power, right, obviously e to the I 2 pi over 3 to the third power, a power of a power multiplies the powers. So that's the same as just multiplying the exponent by 3, which cancels, which gives us e to the I 2 pi, which is equal to 1. So these really are the third roots of unity. So if you want to know, well, what are the cube roots of 1? Well, 1 is the only real number that's a cube root of itself. But there are 2 complex numbers that you could also cube to get to 1, in the same way that there are 4 complex numbers you could take to the 4th power to get to 1. And similarly here for the fifth roots of unity. There's 1, there's e to the I 2 pi over 5, e to the I 2 pi over 5 times 2 is right here, times 3 would be here, times 4, and times 5 takes us back to just e to the I 2 pi, which is 1. Notice that they're evenly spaced at an angle of 2 pi over 5, and again they all fit on a regular polygon this time. It's going to be a regular pentagon. And you can continue this on. There's nothing special with the numbers 3, 4, 5. You can make this as high as you want. And what you'll get is some, extensive polygon with many, many sides inscribed in the unit circle. And it forms a nice cyclic group of order n. By the way, yes, this is the generator of the group. This is the generator of the group. It's always the first root of unity not equal to 1, going counterclockwise. And that might not be the only generator. For example, here, in the case of the fifth roots of unity, and also, I guess, in the case of the third roots of unity, anything other than 1 will actually serve as a generator. But that's more going off into group theory. This is supposed to be a complex analysis class, so I won't get into that. But it's just nice to see these kinds of constructions. So in general, you can do this for any n, and that means what you would consider is e to the I 2 pi over n, and then you would take e to the I 2 pi over n multiplied by 2 up in the exponent, and then multiplied by 3, by 4, and so on. In general, e to the I k times 2 pi n for all integers k, running from 1 through n, until you finally get to e to the I 2 pi over n times n, and of course the n's cancel and you just end up with e to the I 2 pi, which is equal to 1, the identity element. And this first guy is always a generator. It may not be the only generator, but it is always an example of a generator. This collection of n numbers are called the nth roots of unity. They form a cyclic group of order n. They're all generated by that first element. They all lie on the unit circle. They're evenly spaced. They do form a regular n-gon. So we saw that. Any one of them taken to the nth power will give you 1, right? So in general, these are all numbers of the form e to the I 2 pi over n times k. If you take that to the nth power, again, taking a power to a power just multiplies. So that's e to the I 2 pi over n times k times n. Well, the n's cancel, and that just leaves you with e to the I 2 pi k. But any integer multiple of 2 pi just means that we've wrapped around the unit circle k times, and it always takes us back to 1. k full revolutions always brings us back to 1. And in fact, it turns out that not only are these all, nth roots of 1, they're the only complex numbers that will give 1 when raised to the nth power. They're the only nth roots of 1. So here's how you can see that. If we write r e to the I theta as some random number and take it to the nth power and we expect to get 1, well, 1 is equal to 1 times e to the I 2 pi, right? I mean, its length is 1, so there's really no need to put that even. And its angle is 2 pi, or remember that, this is the same as e to the I times 0, or e to the I times, instead of 2 pi, 4 pi, or in general, e to the I 2 pi k for any integer k. Because it just means you've made k full revolutions around the circle and it always gets you back to 1. So these polar coordinates are not unique in general. But anyway, going the other direction, r e to the I theta taken to the nth power, well, that n distributes to both, and it looks like this, r to the n e to the I n theta. Again, power taken to a power multiplies the powers. Alright, so in particular, the lengths have to match up. So Rn had better equal the length here, which is just 1. So Rn equals 1. But remember, r is a positive real number. R is not some complex number. R is the length of the vector, which is a positive real number. So the only positive real number you can take to a power and get 1 is 1 itself. So r equals 1. So that already proves us that the length of anything that's an nth root of unity must lie on the unit circle. It must have length r equal to 1, modulus equal to 1. Also, we know that the arguments have to match up. E to the I n theta had better equal e to the I 2 pi, just like this, which means that n theta has to either equal 2 pi, or it has to equal, so I put mod 2 pi here, you don't have to worry too much about what that means, but it has to equal some integer multiple of 2 pi. So n theta is either 2 pi, or it's 2 times 2 pi, or 3 times 2 pi, or something like that. Alright, so suppose that it is. Suppose that n theta is equal to 2 pi times some integer k, which is what we would need to have happen for this to be an nth root of unity. Okay, then just moving things around, divide both sides by n, that means theta is equal to 2 pi over n times k. And isn't that exactly the angles that we were dealing with here? 2 pi over n times some number k, some integer. So what we did is we ran those integers k from 1 to 2 to 3 dot 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 in general all the way up to n. Right, so these will be different as k runs from 1 through n. They will, if you draw the unit circle, what they'll do is they'll hop across the unit circle at even spaces as k runs from 1 through n. But once k actually hits n, you get to 1. You get to the number 1. And then when you go to k equal n plus 1, you're repeating yourself. And then it just repeats itself. So that's how we can see that these are in fact the only nth roots of unity. So it's a nice little blend of group theory and complex analysis.